Hello, good afternoon. I'm Michael Ocampo from Astera Labs Ecosystem Alliance Manager. And we have,
Hi, I'm Ahmed Medihoub. I'm the product manager for our CXL Memory controllers.
all right. Thanks for coming. Our topic for today is optimizing AI inferencing with CXL Memory. So as we were putting together this presentation, I actually put a prompt into Llama 3 or Meta improving GPU utilization with CXL. And this is the actual first image that popped up, which is pretty interesting because it shows a bunch of cables and servers and a rack, which is pretty interesting because in our booth, Astera Labs B13, we actually are showing CXL as well as PCIe cabling, both active electrical cabling as well as active optical cabling. So I thought it was a very appropriate picture to just include into the intro slides, but the core topic, right, is really what is the value of CXL in the context of AI inferencing. So we'll talk about the memory requirements, the evolution of AI inferencing servers, and how we are optimizing it. And then Ahmed's gonna cover CXL benefits for DLRM, which is another popular AI inferencing workloads for a lot of big hyperscale companies. It's particularly for ad revenue business. And then at the end of the talk, we'll have some calls to action. So I think a lot of people talk about AI training, and I think the focus has really shifted to AI inferencing. And ChatGPT comes to mind, but there are other types of LLM inferencing workloads that are kind of similar to ChatGPT, right? GPT-like applications including OPT, Open Pre-trained Model, Llama, Mistral, etc. And one of the things that you find as you're looking at this chart on the bottom left, this diagram is actually from last year's OCP by Dan Rubinovitz. And you can see that AI inferencing is very, very memory capacity, bandwidth constrained, as well as very latency sensitive. So actually, it's quite interesting when you look at how ChatGPT and other things like that are being used. Like for example, my son, he'll say, hey, I wanna create a new story. So he becomes the main character in the story, and his stuffed animal become his like friend in the story. So it's generating a lot of information, tons of tokens that have to be remembered and kept into the memory as he goes to sleep. So as you can imagine, it takes a while for an 8-year-old to go to sleep. So the story keeps going on and on and on. So I thought this was kind of an interesting story to tell because that is what we call KV cache. That requires a ton of memory. And every service has different context window. And context window is limited because it comes at a cost. Comes at a cost of memory. And some servers may only have very limited amount of memory. 768 gigabytes is pretty typical. So I think that's one of the main drivers here for not just CXL, but memory innovation in general. So another thing to note here on the bottom right is if you had something like roughly 10 novels, that's approximately 1 million tokens. So that would take up roughly 1 terabyte of memory. So that's definitely exceeding your typical server memory footprint. So if you look at the evolution of what we were seeing in the past and then moving forward, NVMe is a very, very popular caching hardware. And a lot of the computing is done by GPUs. So on the left-hand side, try to make a very simple illustration for how data movement happens, right? In the context of KV cache, as you ask it a question, where does that data go? Is it sitting in memory? Eventually, if you're exceeding the local memory, it has to store it somewhere. So today, that's happening on NVMe. and then you have to feed that information to the GPU to efficiently process this request of telling a story. And so on the right, we wanted to see, okay, what if we were to replace that cache with a much faster cache? That's cache line I/O versus like a 4K read and write operation that you see with NVMe. So we did that test. We have a GPU server from Supermicro based on Genoa, or 4th gen EPYC processors. And what we actually tested is only one socket and 2 L40S and then 2 Leos. But for a baseline, we didn't include the CXL devices. We just wanted to see what would happen if we have NVMe cache and then 2 NVIDIA L40S GPUs. And what we saw was that there was definitely a slower time to insight due to the NVMe cache, and then high CPU utilization, and therefore very limited concurrent LLM instances per server. So of course, when we tried to test this with 2 of our Leo chips, which is our CXL memory controller, with 4 DDR5 5600 DIMMs, we saw 40% faster time to insights, 40% lower CPU utilization per query, and then we can increase the concurrent LLM instances per server. So here's the raw data. So if you look at the characterization of the workload over time, this is the y-axis is GPU utilization, and the x-axis is time. So if you just look at the orange line, that's basically, you can see it finishes after 700 seconds. And you can see the GPU utilization goes up. And mind you, there's 2 GPUs, so it gets up to around 180%. This is because there's 2 GPUs, so two GPUs would effectively be 200% if it was fully utilized. And so that's actually what you see with CXL. It goes up to about 160%, and then goes up to 200%, and then it finishes at 400 seconds. So this is based off of a FlexGen, which is an LLM engine, and this FlexGen software is actually a research project that is from Carnegie Mellon, Berkeley, Stanford, Yandex, and various other R&D researchers. And it was quite compelling, and their whole goal was to see how can we get more utilization out of these GPUs. And so they created this project, and that's what we used for our proof of concept here. Interesting thing to note is that the model size itself is 122 gigabytes. So what was driving this utilization of the memory is actually the KV cache I was mentioning earlier. So the run parameters you can see is prompt length of 512, which is kind of like your question, gen length of 8, GPU batch size of 24, and then the batch size of 12. So that's basically asking it to do that job 12 times. And then FlexGen has an algorithm to basically realign it and try to increase the throughput as best it can with the resources given, regardless of if it's NVMe or CXL or local memory. So it aggregates all those resources and was able to get this kind of result. On the flip side of the coin of this workload, if you take a look at the CPU utilization, it's quite high when it's without CXL. And again, the reason why is NVMe, it's not only just slower, but it's also congesting the CPU because there's a lot of delays and waits for the load store operation. And then with CXL, you can see the utilization is quite low, 25% compared to 65% at its peak. So started theory crafting based on this information. Let's look at this one bar at a time. So if you look at the purple bars, that represents the actual memory requirement for the model. That's the OPT66B model. And then KV cache is basically, you know, both of those combined equates to about 1 terabyte. So to make the math easier, one instance is approximately using about a terabyte of memory. And then so you're seeing all the different tiers stacked up, green, blue, and gray. The gray actually represents the NVMe SSD. So even though the SSD is quite a large capacity, it's actually not using so much because the FlexGen is going to use the fastest tier available. So that was the local memory plus CXL, and then a little bit of the, or sorry, in this case, there was no CXL for the first ones. This is what was driving the utilization 65%. And so without CXL, you can see the NVMe was used versus when you have one instance with CXL, then it drops to 65%. And there's no NVMe usage. Everything is basically loaded in memory and processing efficiently. So if we were to double this up and run 2 instances, based on what you see in the first bar chart, you would have a CPU bottleneck if you try to scale this up, right? Because you have 2 KV caches that you're trying to fulfill in those instances based on that story that's being told. And if you were to scale this up to 4, definitely you couldn't even do that, right, without CXL. But with CXL, we theorized that you'd be able to run 4 instances with some overhead to spare. So there's some more work to do, but essentially that's what we observed, and we plan on running these tests in the future. On future platforms and with more resources. So that concludes my segment. I just have a few wrap-ups here, and then I'll pass it to Ahmed. So what we saw from my segment was 40% faster times the insight with ZXL, 40% lower CPU utilization per query, and therefore we can run more LLM instances on one server.
Thank you. Thank you, Michael. So another example of these AI inferencing workloads are DLRMs, or deep learning recommendation models, typically used in many applications, just like Michael mentioned in the very beginning, Netflix, Google, and others. Now, some of the challenges that these applications have are from left to right, large or huge data sets and huge matrix tables. Partially utilized cores due to data overhead. And with distributed computing, making the right data available to the right node is orchestration intensive. And since some of these DLRMs are still run on GPUs in many cases, and that could be power intensive. So perhaps the largest area of optimization that we can impact with CXL are the data movements, where data is pulled out of the database and prepped in a format that the model can consume. We see that this large percentage of time spent on data movement and transformation can be significantly alleviated simply by adding more memory. So effectively, doubling the memory in the system effectively allows a larger data set to be cached, which inherently shows a significant improvement in performance. We ran this benchmark in partnership with AMD on a Supermicro A+ system, where we have one AMD 5th generation EPYC processor with 12 96 GB DIMMs directly attached to the CPU, and 16 64 gig DIMMs CXL attached, connected via 4 Astera Labs Leo CXL memory controllers for a total system memory capacity of about 2 terabytes. 1 terabyte directly attached, 1 terabyte CXL attached. We see that with about 60% more memory channels added, 133 higher bandwidth we see a little over 70% increase in performance for these workloads. And as we showcased AI inference running on CPUs with high memory capacity and bandwidth in the previous slides, we see servers such as this one, the Lenovo SR860V3 showcased here on the top left, and also in our booth, which were traditionally designed for large in-memory database applications, are now being considered for new applications such as inferencing. This particular server features 4 of the latest Intel Xeon processors with 64 direct-attached DDR5 DIMM slots and 64 CXL-attached DIMM slots via 16 Leo CXL memory controllers, approximately about 4 Leos per socket. That is a total of 128 DIMM slots for the whole system. And when populated with 128 gig DIMMs, we are looking at a 16 terabyte of memory in a single server. So as final remarks, I think would like to invite you to check out our website, all our products that we have in the booth and here, but also get involved in the OCP CMS project to drive innovation. See the CXL technology in action in our booth at B13. Provide input on new CXL hardware designs at the CMS table in the OCP Innovation Village. And for any other questions, you can contact me or Michael directly. And Michael, you can close.
Yeah, definitely get involved. As mentioned, this stuff is awesome. It's in our booth, B13. We also have a mock-up of what we think the next generation AI systems will look like. It actually features all of our silicon, everything from our Leo CXL controller, our Aries 6 retimer, our Taurus Ethernet cabling, as well as our new product, our Scorpio PCIe switch. And then over in the Inventec booth, I think it's actually B8, not B9. This is a CXL box with 96 DDR5 4800 DIMMs. So thank you for them for sharing that with to the world, and thank you for joining us for our talk. And that concludes our presentation. Thank you.
Thanks, everyone.
Thank you for your presentation, and this is very interesting work. I remember that maybe this platform does not have a plan in the status to support the CXL protocol. So you made some CXL memory devices, CXL domain path, and maybe the GPU is maybe PCIe protocol. So my question is that maybe some translation over the CXL domain to PCI.
Yeah, so I think this is in a comment on the FlexGen data, right? Yeah, that's a good question. Effectively, yes, even though the GPU doesn't support CXL, what you're seeing is that the CPU is able to pass information quicker because of the CXL cache line performance, right? Versus 4K random, reads or blocks on the NVMe cache. So that's the reason for the performance, right? We're not proposing or simulating some GPU. We use the L40S GPU from NVIDIA, 2 of them in fact, right? To then feed it as fast as possible.
So to quickly summarize what Michael said and add a little bit to it, the coherence agent in the CPU is the one responsible or given access to the GPU to system memory. So GPU is connected via PCIe, Leo is connected via CXL, but the whole memory is made available through the CPU.
Thank
Does that answer?
One quick question.
Thank you.